Vibration analysis introduction. Sources of frequencies. The three sources of frequencies in machine are generated frequencies, excited natural frequencies, frequencies caused by electronic phenomena. Vibration analysis introduction. Generated frequencies, sometimes called forcing frequencies, are those frequencies actually generated by the machine. Some examples are imbalance, vane pass frequency, or number of vanes times speed, gear mesh frequency, or number of teeth times speed, various frequencies generated by anti-friction bearings, ball passing frequency of the outer race, ball passing frequency of the inner race, ball spin frequency, and fundamental train frequency. Generated frequencies are the easiest to identify because they can be calculated if the internal geometry and speed of the machine are known. Some of the calculated frequencies may be present in most machines without indicating a vibration problem. These frequencies, at acceptable levels without sidebands, include, but are not limited to, imbalance, vane pass frequencies, blade pass frequencies, and gear mesh frequencies. Other calculated frequencies should not be present in any form at prescribed calibration levels. These frequencies include, but are not limited to, ball pass frequencies of the outer and inner races, ball spin frequency, fundamental train frequency, etc. Calculated frequencies should not be modulated with any degree of significance by other frequencies. If any of these frequencies are generated, a vibration problem exists. When a rotating unit has a mass imbalance, it will generate a sine wave that has very little distortion. This signal can be observed in the time domain. The frequency domain spectrum will have a spectral line at 1 times speed of the unit. For example, a 1776 RPM fan that is out of balance will have one spectral line at 29.6 Hz. Most pumps and fans can generate vane or blade pass frequency, which is the number of vanes or blades times the speed of the unit. A high vibration at this frequency could be the result of buildup on the vanes or blades, the vanes or blades hitting something, or looseness associated with the rotating unit. Example 1. What is the blade pass frequency of a 1776 RPM fan with 4 blades? And the answer is 1776 RPM divided by 60 equal to 29.6 Hz. And 29.6 Hz multiplied by 4 blades equal to 118.4 Hz. Gear mesh frequency is normally seen in data taken from a gearbox or gear train. The frequency is the number of teeth on a gear times the speed of that gear. For 2 gears in mesh, the gear mesh frequency will be the same for each gear. The ratio of number of teeth to gear speed is a constant. In a gear train, all gears will have the same gear mesh frequency. This vibration is caused by teeth rotating against each other. Multiples and submultiples of gear mesh frequency are sometimes observable in the frequency spectrum. Example: a bull gear with 67 teeth is in mesh with a 22-tooth pinion gear. The bull gear is rotating at 6.4 Hz. A. What is the gear mesh frequency? GF. B. What is the speed of the pinion gear? And the answer is gear mesh frequency, GF, equals to number of teeth multiplied by gear speed. A. Gear mesh frequency equals to 67 multiplied by 6.4 Hz, equal to 428.8 Hz. B. Since gear mesh frequency, GF, is the same for both gears, the speed of the pinion is 428.8 Hz divided by 22 teeth equal to 19.5 Hz. There are many other generated frequencies such as misalignment, bent shafts, bearing frequencies, looseness, etc. Vibration analysis introduction. Excited frequencies. natural frequencies, are a property of the system. Amplified vibration, called resonance, occurs when a generated frequency is tuned to a natural frequency. Natural frequencies are often referred to as a single frequency. Vibration is amplified in a band of frequencies around the natural frequency, as in Figure 1. The amplitude of the vibration in this band depends on the damping. When we refer to the natural frequency, we often mean the center frequency. Natural frequencies can be excited by harmonic motion if the harmonic motion is within the half-power points of the center frequency and contains enough energy. The half-power points are down 3 decibels on either side of the center frequency. The frequency range between these half-power points is called the bandwidth of the natural frequency. The half-power point, or 3 decibels, is 0.707 times peak at the center frequency. It is a general rule to stay at least 10% away from each side of the center frequency. If some frequency is within the bandwidth of the natural frequency, and this frequency contains enough energy to excite the natural frequency will be present. The term critical speed means the rotating speed of the unit equals the natural frequency. When this occurs, the natural frequency is considered unacceptable by some experts. Damping is the measure of a machine's ability to absorb energy. Therefore, a relatively undamped vibration signal can be high in amplitude and relatively narrow-banded. A relatively damped signal can be low in amplitude and relatively wide-banded. Figure 1 displays a relatively damped frequency. Fc is the center frequency and is equal to 18 Hz. F1 is the low frequency at the half-power point, 0.707 times peak, and is equal to 14 Hz. F2 is the high frequency at the half-power point and is equal to 22 Hz. From this information, an amplification factor, AF, can be calculated. Amplification factor equals to center frequency divided by F1 minus F2 equals to 18 divided by 22 minus 14 equals to 18 divided by 8. Or amplification factor equals to 2.25. Some experts agree that the amplification factor should be less than 8. Note that the result is the same if RPM is substituted for Hertz. Some standards for fluid film-bearing machines require an amplification factor of less than 8. However, for rolling element bearings, it is hard to get less than 12. Natural frequencies can be helpful when they act as a carrier, transporting the source of excitation to the measurement point. This normally occurs when natural frequencies are excited by periodic motion such as hits, bumps, or impacts. In such cases, the natural frequency can be present with spectral lines on each side. The number of these spectral lines, or sidebands, is determined by damping and distortion of the waveform. The difference frequency between the spectral lines identifies the frequency or source of excitation. More than one natural frequency may be present, and harmonics of the natural frequencies can occur if distortion is present. Vibration Analysis Introduction. Natural frequencies and resonant condition. Natural frequencies can be identified because they are generally not a calculated frequency, but they are modulated by a calculated frequency. An excited natural frequency is a resonant condition. Resonance in rotating machinery is the same as an amplifier in electronics. Therefore, excessively high vibration amplitudes are often encountered. The resonance and deflection calculator program is necessary in every predictive maintenance program to identify and calculate natural frequencies, critical speeds, mode shapes, and wavelengths. Critical speeds and mode shapes require some explanation. For explanation purposes, we shall use a simple H-beam. The theory applies to more complex systems such as motors, turbines, gears, etc. A critical speed occurs when a machine speed equals a natural or resonant frequency of the machine or some machine part. The mode shape explains the way the beam or machine is bending. The first mode equals the first critical, the second mode equals the second critical, etc. The second or higher critical are seldom a harmonic of the first or higher critical. The wavelength or lambda is the physical length of a beam required for one cycle to occur. The wavelength should not be confused with the natural or resonant frequency, because the natural frequency occurs at 1/4 or 3/4 of a wavelength. The reason for this seeming paradox is loops and nodes. A node or a nodal point is the place where the curve crosses the 0 point. A loop is the area where the curve is not crossing 0. Zero motion or vibration occurs at a node, and maximum vibration occurs at the peak of a loop. Following are some simple rules to remember when working with resonant frequencies. 1. Mass. If mass is added, the frequency goes down. If mass is removed, the frequency goes up. 2. Stiffness. If stiffness is increased, the frequency goes up. If stiffness is decreased, the frequency goes down. 3. Increase in length lowers stiffness. 4. Decrease in length increases stiffness. 5. Braces increase stiffness. Vibration analysis introduction. Frequencies caused by electronic phenomena. Clipped time signal. Square wave. Distorted waveform. True harmonic content. Pure imbalance. Physical nature of vibration. In certain situations, false or misleading signals can be present. For example, when a sinusoid is clipped, as occurs when the input to the real-time analyzer, or RTA, is overloaded slightly, it can cause a string of harmonics. The amplitude of the harmonic content is normally quite low, as in Figure 2, clipped time signal. If the clipping is serious enough to cause a square wave or near square wave, only the odd harmonics may be present, or the odd harmonics can be higher in amplitude than the even harmonics. See Figure 3 square wave. Also, if a sinusoid is distorted and the time period for each half wave is not equal, harmonics can be generated as in Figure 4 distorted waveform. When true harmonic motion is present, the number of positive going peaks observed for one time period is equal to the true harmonic content. The amplitude of these harmonics is normally high in the frequency domain. When distortion occurs with true harmonic content, the number of harmonics in the frequency domain can exceed the number of positive peaks for one period in the time domain, as in Figure 5, true harmonic content. If the construction of a machine is sound and the various parts are not defective, the machine will behave in a linear manner. Pure imbalance will generate a single frequency without harmonics or modulation, as in Figure 6 pure imbalance. There are several forms of nonlinear problems in a machine. Misalignment, for example, is nonlinear and is not speed-related above certain speeds, depending upon shaft size, coupling type, amount of misalignment, etc. It is general knowledge that at higher speeds, less misalignment is allowed. After the speed increases, making misalignment a problem, the vibration level will increase to a given point and remain relatively constant at higher speeds. Looseness is probably the most common form of a nonlinear machine problem. Looseness is also the most common problem in operating machines. When some form of looseness is present in a machine, the machine becomes tuned for maximum sensitivity. When this occurs, a small amount of imbalance can cause high vibration levels. Also, the machine is easily shaken by a small excitation from other machines. Looseness causes distortion in the signal. The distortion causes harmonics, And if clipping or truncation occurs, sum and difference frequencies will be present in the spectra. A good time domain signal is necessary to identify all frequencies in the frequency spectra and accurately diagnose machinery problems. Thank you.